Welcome everybody to session 3 of Hack Summer 21. My name is Taggart, and tonight we are taking on networking in the Linux environment, but also just computer networking in general. So not really a whole lot of preamble for this one. Let's jump right into the material. We have a lot to do today, so let's get started. So we're going to start at the very basics. I'm assuming no prior knowledge of computer networking for this session. So there are going to be some terms that come up, and I'm going to do my best to define them as I go. But if I miss something or something needs a little bit more explication, please don't hesitate in chat to shout them out. And especially if you are studying as ABC-WAN maybe or has done in the past for a certification like the CCNA or the Network Plus or even the Security Plus, don't hesitate to shout out those questions. I want to make sure that I do, well, I give information that you need. So that's what we're here to do. So make sure that I'm hitting what you need from this. But right, let's start first of all with a little bit of, there we go, just a little bit of music in the back. But let's start with the very, very basics of computer networking, right? How do computers talk to each other? And the real basics are that you have two computers, right? One sends a signal to another one, the other one receives that signal and interprets it and sends signals back. Let's take computers out of the equation for just a moment and think very simply about some of the most simple communication methods that we have, radio, but even simpler, think about cans on strings, right? If we have a wave of information going in one direction and then it comes into the other end of that connection, it can be received, interpreted, and then another signal in the form of a wave sent back. So really at the very, very lowest level, and there's a reason why I'm starting at that very lowest level, what we're talking about is waves or electrons being sent over a wire, a connection between 2 points. That's the basic of computer networking. It's no different than any other kind of communication. Now, in the specific case of modern computers, some interesting stuff goes on there because it's not just raw electricity that we're dealing with, right? The raw electricity is going to have to be interpreted in a lot of different ways. And so as we move upward from those electrons, there are different both hardware and software components that go into how networking works. An important term that you're going to hear a lot tonight and throughout networking is the network interface. Signal senders and receivers are called network interfaces. And so I want you to think about that idea of a network interface as anything that connects you to a network, whether it is the Ethernet cable that you plug in, or whether it is the kick recording on just in case. Whether it is the network cable that you plug into the back of your computer, or even the wireless radio that you use to connect to Wi-Fi. Both of these would be considered a network interface. For those of you who are dealing with buffering, I'm really sorry about that. I can see that I'm dropping some frames here. So hopefully it'll get better in a minute. If it doesn't, I am recording this one just in case. So worst case scenario, I'll put up the recording on YouTube and it'll be fully watchable without any buffering later. Now, once we get into that network interface, once we're sending signals through that network interface, we have to ask a couple of questions. First of all, how are the chunks of information that we're sending back and forth, how are they being routed, right? How do they know where to go? And then once they arrive at their destination, how are they being interpreted? Something that I thought was pretty cool that I wanted to put over in this slide was the log of the very first DARPANET communication ever. So when the internet was very young, before the modern internet, we had the DARPANET, which was a connection between a bunch of universities on the West Coast, basically. And here you have October 29th, 1969, at 22:30, we had the connection to the SRI, the Research Institute. And that was it. That was the first communication. All right, let's move on. So in modern networking, what we're going to talk about with computers is pretty much IP networking, Internet Protocol networking. So let me show you what that looks like in our Linux environment, and then we can kind of move forward and explore how we can use IP networking and the cool things that we can do with it in Linux and how we can configure it. So the first thing I'm going to do is come over to my command line interface, and I have VirtualBox on. I have my virtual machine running. And from here, I am going to simply run the first command ever for networking, which is IP. It used to be IP or IF config, but these days we do IP ADDR or IP address, but IP ADDR will do. And if you're on the Linux VM that we've set up together for this course, you're going to see a lot of information here that is kind of intimidating. It doesn't make a whole lot of sense just yet, but that's okay. We're going to break it down. The first thing that you need to know here is that we're looking at 3 distinct network interfaces. We don't need to worry about their names just yet, but there are 3 distinct network interfaces. These network interfaces have names that indicate the kind of network interface that they are, and then there's a whole bunch of information about how they're configured. What we want to focus on right now, though, out of all this information that comes back from the IPAdder command, is this INET number right here. This INET number right here is what we usually call our IP address. And notice that there's an INET and an INET6. We'll talk about that in a moment. But I want us to focus on the INET number here. Now, you probably have seen numbers that look like this before. This is an IP address. And even if we use basic networking tools that you may have even used before, you're going to see these IP addresses all the time. If any of you are on a Mac, there's a cool thing that you can do, in case you didn't know this. If you hold down the Option key and click on your Wi-Fi icon, you'll actually get a whole lot more information about your internet connection, your network connection, and one of the things you'll see is your IP address. You'll see some other stuff too, but including your connection strength, which is really, really handy, but you'll see your IP address right there if you hold down the Option key and click on your Wi-Fi icon on a Mac. Windows, right, if you're on a Windows machine, you can kind of find out your IP address using, if we're in a command prompt, you can do like ipconfig, right? And you'll get very similar information to what we just got in Linux, but in the Linux world, it's going to be IPAdder for modern Linux distributions. So these IP addresses are how our computer is referred to on our local network, and we'll talk about the difference between a local and a wide area network in a second. But these identify our machine on the network, and every network connected computer has one of these. Let's prove that point. I'm going to go ahead and ping ubuntu.com. And actually, if you want to play along, if you do this on Windows, it's just ping, but on Linux, we're going to do -C4. Orbital, thank you so much for the subscription to FieldEd. Really appreciate that. If we ping with a count of 4 to ubuntu.com, there's some other stuff that's going on here, but you'll notice that what we get back from davybones.canonical.com is a response from a number that looks very much like, in shape, the number that we had up here, right? Some numbers, a dot, numbers, dot, numbers, dot, numbers. So this is the IP address of the computer that we pinged. We pung? I don't think that's right. That we pinged. And that gives us some information about it. as a matter of fact, you can even, this is a little bit beyond the scope here, but you can do something pretty cool where you can actually take that and run it against Whois. Whois isn't installed. We can play with that in a minute. You could also just use the online Google Whois and look up to whom that IP address is registered. But the point here is that we're looking at an IP version 4 address. VLAN tag 69. No. Okay, so let's talk about the IP protocol, the internet protocol. I hate when people do that. Like the ATM machine. Let's talk about the internet protocol, or IP. This is how most devices communicate over the network. There are other protocols, and actually, if we are being super technical, it's TCP/IP that we're talking about, because the transmission layer and the data link layer are related, but the network layer and the transmission layer are related. And to that point, the internet protocol is only one part of the networking stack. As we said, moving up from those raw electrons all the way up to what you see in your web browser, there are many different layers of technology that we have to deal with. And as we said, IP addresses are assigned to each device on the network. You might ask how. Generally speaking, there are two ways in which an IP address is assigned to a computer. The most common way these days, if you connect to, coffee shop Wi-Fi or even the Wi-Fi at your house, right, is you would have, you attempt to join the network, you're authenticated through the wireless, and then some other process kicks off, and that some other process is called Dynamic Host Control Protocol, or DHCP. And what DHCP does is it says, hey, I'm here, I'm on the network, give me an IP address. And the DHCP server on your network will look through its pool of available IP addresses, select one, and give it to you. And that is how you generally would receive an IP address over a normal DHCP-enabled network. But that's not the only way. The older school way of doing it is by statically assigning your IP address. And in many cases, that's how you want to set up your IP address for really sensitive devices. So things like your domain controller in a Windows environment, or file servers that you don't want to have their IP change, you can statically configure their IP address using the built-in networking tools. I'm seeing that there's a long delay in chat, yeah. If I refresh it, we'll see if we can do any better. Okay, now we talked about there's IPv4 and IPv6, and sure enough, what we were looking at before was the IPv4 addresses, right? Number dot number dot number dot number. But you're also going to sometimes see IP version 6 addresses, which have colons in between the 4 hexadecimal character chunks. They're not octets, but segments of the address. Now, IPv6 is a newer protocol, and it really hasn't caught on because it hasn't had to. But we'll talk about why it exists in general. But nevertheless, we're going to focus on IP version 4 addresses. And we're going to go into Vim to visualize a little bit of this, but let's talk about what we're looking at when we look at IPv4 addresses. So the first thing that we need to know is that it's 32 bits of information. 32 bits of information. That's what the entire IP address is. It's separated into 4 8-bit sections called octets, right? So every 8 bits, and then there's a dot. And we represent those numbers in decimal because it's easier, but they are made of 8 bits. Let's go into Vim quickly to try to visualize that. So I have 1, 2, 3, 4, 5, 6, 7, 8 dot, and let me awesome. Because NAT, yes, network address translation is why we haven't needed to go IP6 everywhere. So here are the 32 bits that make up an IPv4 address, right? Now, we could take any one of these, right? And again, we're talking about binary, so remember that what we're talking about something where we have this is the ones column, twos, fours, 8s, 16, 32, 64-bit, 128-bit. So essentially the maximum value for every one of these octets is 255. That's the maximum value for each one of these, right? So quick math here, right, is that, let me bring up calc because I always forget what the number is. But nope, give me scientific. Yeah. Right? You might think it's not actually 256 value. So 255. Where's my exponent button? Nope. Oh, there it is. I've never used this. 255 exp4. No, that was engineering. That didn't help me at all. Forget this. Let's go to Python 3. 255 fourth. There you go. That's how many potential IP addresses there are in the IPv4 space. Now, that's actually not enough for all the devices in the world, but we use local networks and wide area networks separately, and these addresses can be reused again and again and again. For example, on your home network, your IP address probably looks something like this: 192.168.something.something. Well, lots of people are going to have IP addresses in their local network that look like this. But your router on your home network has an inside and an outside, right? The inside is where that local IP address makes sense. But your router also has an external IP address that connects it to your internet service provider. Now that has an IP as well. And if you Google, I'm not going to do it because I'm not going to dox my own IP, but if you Google what is my IP, or you go look it up with some other tool, you are going to see your public IP address, which is not going to look like that 192.168.whatever.whatever. So that is that segmenting of networks is one of the reasons why we haven't needed to go to IP6 yet. But as Angel says, we're still running out of IP4 networks, but we can talk about that in just a minute. So here's the deal. We don't have to use all of this. So if you think about how large that space is, what we just discovered, right? We don't need that many IP addresses in any local network. For that reason, what we do is we mask off some of the available IP address space, and we say that we're not going to use it. And the part that we do end up using is called a subnet. So we're going to talk about subnets for a little bit here, just so that everybody's on the same page with this. Okay. Now, as we've seen, your IP address might look like 192.168.something.something. And that last octet, and I'm going to say this we're going to focus on this last octet to start, is available, but the last one is, but the rest of the address is locked or masked. For example, in your local IP address space on your home network, you're never going to see this 0 turn to a 1 Probably. It could, depending on how it's configured. But most home networks only have this last octet available. So let's go into Vim and explore how that actually works. So an IP address has to have associated with it a subnet mask. So again, we're going to take this idea of an IP address like 192.168.0.1 or 10, whatever it is. And we're going to say, so the address is this. And we're going to say that the subnet mask is, well, we're going to write it two ways. 255.255.255.0 is the long form. We can also say that it is a 24-bit subnet mask or /24 network. And what we're saying here is, okay, how many bits of the 32 are unavailable, are masked off? Well, we know that there is 8 bits in this octet, so that's 8, 16, 24, leaving the final 8 bits. So that's why we have that /24 syntax. So what we're saying is, right, with 24 bits or this 255 value masked off, is that no values in this octet are available in the subnet. None of the values over here are, none of the values over here are, but because we put a 0 in the mask here, right, we're leaving that entire octet exposed. So we're saying the entire range available there is exposed. I have an interesting question if you have time. Why are some 172 addresses public and some private? That's a good question. Fielded. This is going to take going to a web browser to answer. So let me bring up a... Networks have classes. And they don't always play by the rules when we create local and public networks. That is true, Angel, there are non-routable network ranges, which are Usenet ranges. But to Angel's point, a lot of internal networks will use a 172.16, except that's actually meant to be a Class B network. But it just isn't, because for what it may be, when the internal network engineer was setting it up, they decided to use a 172.16 because it was going to be a larger network for whatever reason. But formally, a Class C network, which is meant to be kind of an internal private network, is supposed to begin in the 192 block and then move up from there to the 223. Not everybody sets those up that way, though. The other name, by the way, while we're here, that /24 that you saw in that syntax before is also known as classless interdomain routing, or CIDR. All right, so we have this subnet mask, and what that tells our networking equipment and our software is that subnet mask defines our local network. And in order to access IP addresses that are outside of that subnet, something else has to happen. What is that something else? That is why we have that's why we have gateways. So when a packet is, or a piece of network information is addressed to an IP outside of your subnet, it is routed to the default gateway, usually. This will handle the next step in the routing. And this could be a pretty long chain if you want to see how this works. And we can play with this a little bit with a tool called traceroute. Angel, full CIDR notation is IP slash the subnet mask. So let's actually go through that before we go any further. So let's talk about CIDR notation. Right. So for CIDR notation with what we had above, the CIDR notation would be 192.168 for the whole subnet would be .0.0/24. That would be for the subnet itself. Hey, Socialist, good to see you. Thanks for popping in. If we were speaking about a specific address, it would be 192.168.0.say5. But we still want to have that /24 because we need to, this is essentially a shorthand version of saying this is the IP space, and by the way, the bottom of the subnet is likely also going to be the default gateway. Not necessarily, but usually. Now, it can be a different value. So this subnet, this 24, has the potential range of 192.168.0.1 to 192.168.1. You might think 255, but technically it's 254 because the last address is special. It's a broadcast address. So these are the potential IP addresses in that space. But we could actually mask it off even further, right? Because let's say we made a /25 subnet. What would that look like? Well, let's play with that just for a moment. Right, so a 25 subnet changes this up a little bit because a 25-bit mask means that we have 255, right? 255.255, but then, oh crap, what happened here? If we have one extra bit set off, right? That 25, and the zeros and ones, we'll put it above for a second. So these are the zeros that make up that octet. If I turned this into a 1, now all of a sudden this value is not 0, it's 128. Which means that more addresses are masked off. Meaning that if I start my subnet here, my maximum value is not 254, but in fact 127. Or actually 128. That is how subnet masking works. And as a matter of fact, another way to describe a single address in full CIDR, right? If I wanted to describe the address itself, would be /32. To say that is a single address with a /32. Meaning the entire subnet is masked off. We're just talking about that single IP address. I'm going to save this as notes.txt. And we're going to install a tool here to play with this a little bit. And this is the first time that we've installed an application in this course. So play along with me here. This is the first time we've done this. We're going to run sudo apt install -y traceroute. And go ahead and enter your login password for your sudo user. Traceroute is a really neat tool that allows you to see the routing steps that take place for packets of information on your network. So for example, if I were to run traceroute to ubuntu.com, Some of these are going to get masked off, I think, but not all of them should be. Okay, or they will. This doesn't work as well as it used to. We'll try one to google.com, just in case. This is not Golgothus. This is not WSL2. This is, but I'm actually using the Ubuntu VM that we set up, and that's actually probably where we want to go. Let's see, ubuntu.com. I'm going to see if it works on the Windows side. Yeah, there we go. The problem was routing. So this is the Windows version of it, which is TraceRT. So you can see here, if you do it from the Windows side, this actually works. Thanks a lot. Thanks a lot. That's a DNS thing, by the way, is the issue. But you can see the entire path down to my destination, which really gives you a lot of information about how your network is working. Or in my case, how my network is not working. Now, if you want to see how routing is set up by default on your machine, yeah, on Linux, it is... Yeah, TraceRT is not a thing on the Linux side. It's traceroute on Linux. But if you want to see how your routing is configured, that IP command that we used before has a whole bunch of subcommands. One of them that we used was adder, right? But another one is route. Or if you really want to get fancy, IPR. IPRoute and IPR give the same information. So you can see here, I have a default gateway. That's my default route. Where we have 10.0.2.2 device, and this is the name of the network interface. And this is the source IP address. This is my IP address. But this is where the default gateway is, right? It's not the .1, it's the .2 on this subnet. And here you can see that this /24 is being routed right through this network interface, and because that network interface has this default route, then that's how we proceed. Now we also have this other network interface that we haven't talked about yet, but it's here, and network address is going to 172.17, this subnet, this pretty large subnet. Notice the 16, right? Half of the IP address space is available, is heading to this other destination, which we'll talk about in a later session. But that's how we can look at IP route. It's also how, is it just IP route help? Yeah, IP route help. It's also how you can add routes. Similarly, we can add IP addresses. But in order to do that, in order to add an IP address, we actually have to use that CIDR syntax. Let's play with that, actually. Let's play with that. So IP link, add link. Okay, I strongly recommend not playing with VLAN IDs right now. But we are going to add an IP address to this interface. And we're going to add that class C. So we're going to add a 192.168.0. something. To do that, first of all, we're going to have to use the sudo command. But we're going to do sudo IP adder or address add. And if we just run that, it kind of helps hint us through, right? Dev is the device we're going to add it on. And P0S3. Yes, I agree, Angel. VLANs would be, and network segmentation would be a great talk to do. That's kind of like a next level thing, but I absolutely agree. It should be done. Especially because a lot of people misunderstand that VLANs by themselves are not segmentation. VLANs plus ACLs can be segmentation. So sudo IP address add dev. So here's our MPOS3. And we have to give it an IP address, 192.168.0.5/24. And now, if we look at our IP A, and S is for show, so IP adder show. Now, look, my network interface has two different IP addresses. One of them is the default one that was provided by DHCP. That's why it says dynamic here. But the other one was added by myself. Now, this is a super temporary way. This is a super temporary way of adding a network or an IP address. If I were to restart the machine, or even if I were to restart the networking service on this computer, on this virtual machine, that IP address wouldn't survive. So I want to show you how to actually set IP addresses for real. Are they real IP or alias? Well, it doesn't. They'll receive traffic on it, sort of, right? As soon as ARP takes over, we'll talk about ARP in a second, but they're real for the purposes of usage. I'm not sure. You could have a conflict if, like, DHCP doesn't know about this IP address, right? So you could have a conflict on the subnet if you take somebody else's IP. But it's real for all intents and purposes. Now, to get rid of that thing, you would do sudo IP address del, and then keep everything else the same. And now it's gone. Now, to set it correctly, what we're going to do, we're going to play with a completely different network interface so that we have an extra network interface that we can play with. You can use another computer's IP as an alias as a mean of man in the middle. Not real. Well, again, so you can. You're getting into like ARP cache poisoning, Angel, at that point, which is a little bit beyond what we're talking about here. So what we're going to do, if we want to fully configure a network interface, we're going to actually go into VirtualBox, and we can just right click on this and go to settings, and we're going to go to the network section here. Oh, we'd have to power off the machine to do this, huh? I was so used to working with VMware where you don't have to do that. Forget it. We'll do it with the up interface. It won't matter because we're going to change it back. So here's what we're going to do. This is very specific to Ubuntu, what we're about to do. Fedora and other Linux, Red Hat, other Linux distributions have other ways that they now configure their networking. But the way that Ubuntu, since I think 1804, has done this is a tool called NetPlan. This is the official way to do it. So NetPlan is pretty interesting, and I don't know how many people actually use this outside of, Ubuntu people, but let's take a look at this. So we're going to do ls/etc/netplan. And you're going to see that there's this YAML file in here that has, once we look at it, it's going to have some configuration. It says installer config. It's basically like the default here. Now, they're numbered because we could add additional YAML files and they would be set up in order. So we could add additional ones there if we wanted to. Everything in that etc netplan folder will be used by netplan when we run the netplan commands. But let's start by looking at that default, or that installer config YAML file. So we're going to vim etc netplan 00 installer config YAML. This is the default config. Look at this. So here's this is the way that it is described. It's a lot easier, I feel like, than older versions of doing this. So you have network, here's your Ethernets. If we had more than one, these would exist here by default after the install, or we could add them later ourselves for a manual. And I'm going to put this link in the chat that there are examples of how to do netplan configs from netplan.io. So we're going to create a static mapping here. So we're going to change the DHCP4. To false. And then we're going to add some other configuration to it. We have to add an addresses key. And of course we can add more than one. We're going to say 10.0.2. Let's say 20. And again, we use that CIDR notation. So we're in a 24 subnet. So we're going to do that. We're going to say that the gateway, the syntax they use is gateway 4. So we're going to give it gateway 4. And if you remember from our configuration before, it was 10.0.2.2. That'll give us outbound. Now we can also set up DNS, which we haven't talked about yet. But let's go ahead and set that up. Name servers. So we're going to use Google's DNS for this, right? And so for name servers, we're going to put in addresses and then use square brackets for a list here. We're going to do 8.8.8.8 and 8.8.4.4. With all of this configured, and I know this is a lot, but with all this configured, we can actually set up a static IP address on our Ubuntu machine. So we've set DHCP to false. We've put in all this extra information that it needs because otherwise it would be getting this from DHCP, but we're not using it. So we have to supply it ourselves. Press escape, save and quit. And now we can do sudo netplan apply. And what this will do is it'll read that YAML file and reconfigure our network service to look just like this. Only problem is I just killed my SSH connection because I was SSH to a specific address, right? At least I think so. That's fine. I mean, it's solvable, but it's good to know, right? That if you're SSH and you do something like this, you might have some complications. Did I utterly break this? Is this the file that overwrites etc resolve_conf on every boot? Resolve_conf is a different thing. etc resolve_conf is just for your name server. It's not for your IP configuration. Yeah, I done broke that. Okay, well, let's go look at this. Let me log into it for real. Or at the terminal. Okay. So it did actually get reset. Boy, it didn't like that, though, at all. So I'm gonna... Let's see, net plan. I'm gonna reset that. So, Feel Dead, you're mostly correct that resolve_conf is overwritten not really by netplan, but by the network manager service. That's what's doing it. Set this back. Oh, okay, cool. And we're back. So that's netplan. And it actually works great. But make sure you know what you're doing with your network address translation before you mess with anything too much. Now, we do have to talk a little bit about DNS, but before we get to DNS, I want to talk briefly about another part of what we see here, which is this big old thing. Now, we talked about IPv6 addresses, right? Like this. And you might think, okay, these look similar, and they do because they have hexadecimal values, but this right here is not... This is not an IP address, this thing at the link ether. This is a media access control, or MAC address. And it is actually one layer down in terms of abstraction. Hey, we're Hacking Live. Good to see you. It's one layer down of abstraction from the IP address. And it's really important because the MAC address... Think about your network interface on your laptop or your Wi-Fi, right? Your Ethernet port on your laptop, if you still have one of those, or your Wi-Fi radio, right? The device's MAC address, generally speaking, it's not totally true, but generally speaking, doesn't change. And blocks of them are assigned to manufacturers so they can be identified. If you've ever run like a network scanner and it shows you like, oh, it's an Apple computer, or it's an HP computer, the MAC address is how that's happening. But the MAC address is important because it doesn't change a lot. It doesn't change generally at all. And so MAC addresses help us answer the question in an IP network, okay, how does the network decide where to send information? Meaning, let's say I have a network of 4 or 5 devices, right? And each computer has an IP address, but each one is connected and has a different... it has a different IP address, but those IP addresses are kind of connected in different ways. Maybe they're on different switch ports if you're using a switched network, or maybe, different just connection sessions on your wireless radio. How does your router or your switch know how to direct the flow of traffic? The MAC address is how that works, because your your router or your switch has a table of references that connects your IP address to your MAC address, saying at this point in time, this IP address on my network is held by this device with this MAC address. And so it looks for where to that MAC address is, and that's how that routing actually happens. That connection, by the way, that determination of who has what IP address, is handled by something called Address Resolution Protocol, or ARP, which Angel was talking about a little bit before. In different subnets, that's correct, Angel. Actually, no, that's not true, Angel. In the same network, it definitely does route. The difference is that if it's in a different subnet, it goes through the gateway, then the gateway forwards it on, and it's routed by the next level up. Yep, the first three, not octets, but the first three chunks are assigned to OEMs. That's right, Fieldhead. So, Angel, to make that a little bit clearer, if I have three, let me see if I can Vim this up. I don't do like whiteboard stuff that often. Actually, bear with me for a moment for an experiment. I want to try this out. It may work poorly, but I want to give it a shot. Awesome. Awesome. Okay. So let's make some squares. And these are going to be computers. Okay? So here are my computers. Yeah. So, and then let's make ourselves a router here, or a switch, actually. The diamond will be our switch. We'll make it like yellow. I don't know why the colors are so weird, but here's the deal. And we'll draw some lines here. So these are all connected to the switch. And now this one has, you know, an IP. They all have IPs. Right? Let's say this one is something 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 dot one, right? That's IP.1. Let's say this one is .2. I'm being very, very general just for speed. And here's .3. Okay. Now, when these all got connected to this switch, this thing started developing a table. This switch started developing a table, an ARP table, saying, okay, .1 is at whatever the MAC address is. .2 is at whatever MAC 2 is. And .3 is at whatever MAC 3 is. And then finally, there's another part here that's really, really important if we're talking about a network switch, which is that each one of these also said, okay, I'm on interface 1. Let me make this bigger. This one says, oh, this one's on interface 2, and this one is on interface 3. So remember, we talked about that network interface is basically how the signal flows, those electrons going through the wire. So here you see the network interface, that's our first layer. The data link, which is kind of how the devices with the network interfaces are identified, that's layer 2. And then the IP address on the IP network is layer 3. So this MAC address table kind of joins all three of those together. And so when .1 sends a packet destined for IP address .3, my mouse handwriting is terrible. The switch is going to be like, okay, this thing needs to get to .3. What the hell is .3? .3 is, okay, this MAC address. Dope. What switch port is that MAC address currently connected to? Oh, interface 3. Awesome. Over you go. And so even inside of a local subnet, you have this sort of routing taking place. Now, the second that, let's say, IP address number 2 asks for an IP address outside of the subnet, it'll be like, okay, what is this? Oh, it's not even in my subnet. I'm going to send that to my default gateway, and out you go. So that's why we have to have that MAC address to IP address, and in the case of the physical networking, the actual interface number. That part is how all of that goes together. So even inside of one subnet, yes, you are getting routed per se, or switched, which is what we do. This is what a switched network does. A minute ago, Socialist, I think, called out Cisco's packet tracer. And if you really want to get your hands dirty with simulating networks, it doesn't get any better than Cisco's packet tracer. And it is free now. You can actually just go get it. You can get a course if you want to sign up for the CCNA prep stuff, but most importantly, if you want to play with creating switched and routed networks, Packet Tracer is an incredible tool for doing so. Okay. Sorry to go like full teacher on everybody with the whiteboard and everything. I'm really sorry about that, but I thought it was a good attempt at an illustration. All right, where were we? So we're talking about address resolution protocol. And one thing that Angel did point out, which I thought was kind of a cool call out. Field Dead, I used to be a teacher full-time. I am a cybersecurity analyst these days, but yes, my heart is still with education, which is why I'm doing this. But yeah, you can take the teacher out of the classroom, but I don't think you can take the classroom out of the teacher. So one thing that Angel was talking about was address resolution protocol poisoning, or ARP poisoning. Let's see if I have any ARP data. ARP-A. Oh, it's not even in there. Of course not. You can try it on your host side too. You can do sudo apt install nettools if you want, and that'll come with a whole bunch of fun stuff, including ARP. And then you can run ARP-A. I don't think there's going to be anything in it except for the gateway. But yeah, you can see here that this is the ARP cache, the address resolution protocol cache on your virtual machine. And so it shows that it has this IP address resolved to this MAC address on this network interface. So exactly what we just said about connecting physical interfaces to MAC addresses to IP addresses. But what Angel was talking about is actually kind of, it's a security thing, is that you can lie about who you are. So you can send, when you do ARP, or the way that ARP works is that computers that need to route something will say, hey, who has this, right? And somebody will respond back with the MAC address of the device with the right IP address. But if you respond first with the wrong, if you intentionally lie about that, you can start sending things to the wrong destinations. And so you might want to check out ARP cache poisoning. It's a pretty cool trick, and it allows you to redirect traffic to IP addresses that you control. Now, I do have TCP/TL. The last thing I want to show before we go forward. Yeah, actually, I do want to talk about this first. So we've talked a little bit already about the layers of networking. And so we're hacking live. MAC spoofing and ARP cache poisoning are two different attacks. They're related, but they're two different attacks. MAC spoofing is where you lie about what your MAC address is, which is a really great way to, for example, get around paywalls on airplane Wi-Fi, because it's using, if you've like already paid, if you found a device on the internet that's already on the local network that's already paid for Wi-Fi, and then you spoof their MAC address, the access point's going to let you on because it's using the MAC address to test who you are. That's a MAC spoofing is a little bit different than ARP cache poisoning, because with ARP cache poisoning, it's like a directionality thing. With ARP cache poisoning, you are lying to the whole network about who you are, and you are attempting to redirect traffic to you. So for example, if I'm on a network, and I'm trying to convince you that I'm a file server so that you can hit my responder or something like that, I will lie. I will say, I will send bad ARP cache, ARP requests or ARP responses out saying, I am that device, right? My MAC address is that file server. And then all of a sudden, devices that are trying to connect to that file server will end up connecting to me. So yeah, we talked a little bit about the way that the networking stack is indeed a stack, and it's layered. And we started down here at the electron level, or the photon level if you're talking about fiber optics. And moving up from that, we talked about the data link layer, right? Talking about the MAC address and how even the Ethernet protocol itself is kind of at this layer here. It's before we get to any sort of what we call, extra encapsulation with the internet protocol or other types of networking protocols, including ICMP or ping, right? There are others, but IP kind of lives at this next layer up. Now, before we get to layer 4 and above, I want to make something very, very, very clear. These layers are not hard and fast. They are abstractions to help you understand how things work, but in real life, that is not really how you end up working with the data. And as a matter of fact, I would argue that the higher up you go on this stack, which is called the OSI model, the more muddy it becomes in terms of what is actually where. Down here, it's very clear when you're just dealing with electrons or just dealing with MAC addresses, but very soon after that, things start to get muddy quickly. Right? When are you working with HTTP and not working with TLS, for example? Or as we said, when are you working with TCP and not working with IP? It's technically possible, but very rarely. And so it's important to understand these differentiations, mainly because they're on certifications. Now, everybody has their favorite mnemonic for these layers because you're going to have to memorize them if you're going for a certification. And feel free to throw your favorite one in chat. My favorite one is please don't nuke the same place again. Physical, data, network, transport, session, presentation, application. Please don't nuke the same place again. And yeah, it's a little, graphic, and I think that's why it's stuck in my head. Dordrek, thank you so much for the follow. Togetsutori, programmers dare not throw away salty pretzels. That's a good one. Now, there's another model that is often used, which is called the TCP/IP model, which sounds like it might be good. But notice that the way that TCP/IP is set up, it separates things into, yeah, ABC1, that's the common one. All people seem to need data processing. And that one goes the other direction, right? PDN, right? Please don't nuke. That starts at the physical and goes up, whereas all people seem to need data processing starts at the application and goes down. Please don't go. We were hacking live. You might be lagging a little bit. That was a mnemonic for the OSI model. Please don't nuke physical data link network. The same place. Transport sensor presentation. Again, application. And yeah, so the TCP/IP model, notice that there's not perfect alignment between the layers. So network access, right, kind of involves some of network, but so does the internet layer as well. And host to host has some transport and some session, but then process application also has some of that. And what you should take away from this is that, again, these are abstractions of the technologies, not pure, dogmatic lines of how the technologies actually work in real life. But it's good to know both of these models. They will both show up on certification exams. Network, internet, host-to-host application or process application. Like now I have a problem. NIHAP. All right, now to show these layers, what I kind of hope we can do is look at TCP dump, which is a really cool tool that is built in. I didn't actually have to install it into our Ubuntu VM. And what we're going to do is we're going to run TCP dump, which is a packet capturing tool, just to see what it looks like, what network traffic, even on an idle machine, looks like. So coming back over to our VM, I'm going to run TCP dump, and let's start with help so we can see some information about it. So TCP dump and -I is going to be the interface that we want to capture on. And we should also generally send this to a file to save, right? So we can do that a couple of different ways, but we'll start just reading it raw and see what that looks like. Now, network stuff tends to require elevated privileges. So we're going to run this with sudo. TCP dump is used a lot by network team and blue team. That's absolutely right. But it's also used, Token Satori, by the red team once they get onto a network. If they can get access to a span port, or if they're on the wireless, right, where they're with a promiscuous mode radio and they can capture all the packets on a network, they're going to be using TCP dump as well. So we're going to do sudo TCP dump. Think of it like Wireshark, but on the command line, right? -I. And if you remember, we had an interface called ENP0S23. Nope, just kidding. ENP0S3. Try that again. Oh my god! Just Control-C to stop that. So what are we looking at here? Look at this. So many things happening. This is SSH traffic, which is understandable given that I'm SSH'd into this machine. And we're seeing all of the packets going back and forth. You can see that there's our IP, right? Gateway, which is the gateway for this network. And there's the host HS21. T-Shark was, Neon, you're absolutely right. T-Shark is Wireshark for the command line. TCP dump is lighter weight, with fewer filtering options as well. Actually, just kidding. TCP dump has eBPF filters, so you can actually do that as well. So that's pretty cool. But yeah, so if I wanted to, I could save this rather than just doing it this way. I could say T and then test.pcap. And then nothing went into test.pcap. That's annoying. That's better. So T didn't work, but direct output redirection did. So if I have that PCAP file. It's pretty low res, but if I want to capture packets quickly, that's a great way to do it. And if you want to know a lot about how networks actually do what they do, I strongly recommend either using TCP dump or Wireshark and starting to read those packet captures and see what's going on back and forth through all the layering of the packets. And again, one thing I don't know if I explained super well, but the packets of information that go across the network kind of get wrapped in these layers. That the data begins as like raw information, but then it gets wrapped in data structures that have information about their intended destination and the content and security information, and all of that is kind of packed up. And then your IP packet is wrapped within a TCP wrapper, which is wrapped within session, which is wrapped within HTML. Actually goes the other way, but the idea is that all of these pieces of data are structured out much like an onion, and that whole structure of layers is what is sent across the network, and then what has to be deconstructed on the other side by the receiving computer. Okay, let's talk about clients and servers. Some new terms here for people who aren't super familiar. So a client, right, is a machine that is making a request of another computer, and a server is the machine that is going to be fulfilling that request. And Linux is very commonly used as a server. That's why we installed the Ubuntu Server Edition when we set up our VM. Now, servers are, the term is a little overloaded. Computers can be referred to as servers, right? You could have a server room or a server rack full of machines that are acting as servers. But a server could also be a piece of software, like an HTTP server that is running on a computer, but the server software itself is what is providing the HTTP data to other computers. And when we talk about services running on a computer or a server, we're talking about those different applications that you can have access to. So network services that are pretty common would include things like HTTP or the web, file transfer protocol, unfortunately even still in 2021, SSH, which we're using now, and then of course things like IMAP and SMTP for mail. So these are pretty common network services. And all of these and more can be available at any one time on a single server, on a single computer. The way that we differentiate between all these services is by a concept called ports. So we've talked about clients, we've talked about servers, and we've talked about services. And there's a lot to understand about how ports work and how like network sockets are generated, which is a little bit next level for what we're supposed to be doing tonight. But generally, let's talk about what a port can be imagined as. It's a number that identifies the service and directs traffic to the right destination. I like to think of it as a channel, almost like a channel on a walkie-talkie, right? I could be sending things to the same destination, but switching the channel, I'll get different information. And there are common ports for different services. So for example, port 21 is very commonly FTP. Port 80 is HTTP very commonly. Port 443 is HTTPS. And let's use our old pal Shodan. As an example here. So I'm just gonna, this is the Shodan search engine. Oh, I gotta log in. Okay, so I'm gonna sign in and I'm gonna say, let's say, look for port. Yeah, let's look for FTP servers, city, Los Angeles. See what we can find here. Okay, so I found in the City of Angels here 356,488 FTP servers. That's, you know, a lot. But my point is, if we look at one of these servers here, this IP address, see, it's all coming together. There's that IP address. If we look at that IP address, you can see that there are multiple open ports. 21, FTP, right? 25, which is mail, 80, 110 for port mapping, 143, all sorts of cool stuff going on here. Now, MySQL, all right. Alt SSH is open. Yeah, 2222. Now, I am not recommending going after and like attacking any of these servers, but I am saying that you can find out a lot of cool information from Shodan, and it helps you understand what these ports mean in terms of services, right? You can see that on 21, we're looking at an FTP server. On port 80, we'd be looking at Apache HTTPD, a pretty common web server. So, and 443 weirdly is Nginx. That's interesting that they use a different web server for their HTTP versus their HTTPS. That's pretty interesting. So, services and ports. If you have any, again, haven't been a lot of questions recently. If you have any questions about how services and ports work, shout them out. By the way, here's a fun one. I think this will work. Is it just allowed? If I'm looking for FTP servers with anonymous login, you have to find out what that banner is. There you go. Anonymous access to the server is granted. Missed some stuff earlier. Any reason you recommend getting familiar with TCP dump versus T-Shark and Wireshark? Neon, great question. The reason I would recommend it is because it's there. It's default on most Linux machines. TCP dump is part of the package, whereas you would have to intentionally install T-Shark and Wireshark. So, from a triage perspective, it's like, oh god, I got to figure out what's going on in this machine right now. You can do a TCP dump and get that PCAP in no time. Whereas you might have to do some extra work to install T-Shark or Wireshark. That's one. Another is, if we put on the red team hat for a second, if I don't want to make too much noise by installing new packages, or maybe I can't install new packages, I want to live off the land a little bit. So if TCP dump is there and I want to see what I can see, there you go. Yeah, Angel's point is also very, very correct. TCP dump would be a great tool for automating the output, and Wireshark for GUI, 100%. T-Shark is good for automation as well, right? Anything you can script through the command line is really solid. And also, just in terms of memory usage, TCP, it's like TCP dump, Wireshark. TCP dump is a much lighter weight piece of software. Fielded wanted me to talk about ephemeral ports. Generally, so bottom line is that there are some services that can essentially establish port connections for a short period of time, bring them down so that there's not just like an always listening service. That's kind of the short version of ephemeral ports. It's pretty cool. Something that you'll see do that all the time is like Windows RPC, or some RPCs, remote procedure call applications will do this. Okay, so the last thing that we're going to do tonight is we're going to set up a web server on our VM here. Now this is going to require a little bit more port forwarding, but we've done some of that. So the first thing we're going to do is we're going to install the Nginx package. So to do that, we're going to do sudo apt install -y Nginx. Now, you can use Apache if you want. I really prefer Nginx. I think it's a much saner web server software, and it's very, very flexible. You can use Nginx as a straight-ahead web server. You can also use it as a load balancer. You can use it as a proxy. You can use it as a reverse proxy. Because of that flexibility, I've really taken to using Nginx in a lot of different ways, and it's served me very well. So I would strongly recommend getting comfortable with Nginx. So when we install Nginx, a couple of things are going to happen that are not just about networking, but they're worth talking about just in terms of Linux stuff. A service has been created on our Linux machine that allows Nginx to start when the operating system starts up and is running right now. To see that, we run sudo systemctl, and let's just run sudo systemctl without any extra commands. This gives us a list of every service and device and everything that's systemd, which is kind of the overarching initialization system of modern Linux OSs, has set up for us. But one of the things in here is Nginx. So you can see that Nginx is available here. If I wanted more details about its status, I could run sudo systemctl status Nginx, and it tells me that it's active and it's running. If I wanted to prove that it was running, I could actually use some networking tricks to find out about it. So I could do curl, which is a very, very important command line tool for networking, right? For HTTP, where we're going to send a raw HTTP request basically to an address of our choosing. In this case, we're going to send it to localhost, which loops back to our own IP. And what we get back is the HTML for the Nginx start page. We've just proven that our Nginx server is up and running. Now, if we wanted to see it in a web browser, there are a couple of ways we could do this. The first way would be to set up port forwarding through VirtualBox, which we've done before to set up our SSH connection. So if I wanted to set up a port forward rule for HTTP, I could say HTTP, and then we'll do the same thing that we did before. Host 0.0.0.0. Host port, let's say, is 8999. The guest IP will send it everywhere, and the guest port would be 80 because that's the default HTTP server service port. Okay, with that set up, I'm really hoping this works. If I go to localhost 8999, I'll see the Nginx page. That's not the only way I can do it though. And this one's special for Angel because he requested it. And I'm probably going to get it wrong my first time because I always get it wrong if I haven't done it for a while. But it turns out that SSH, the thing that we're using to connect to our VM in the first place, has some superpowers. And one of them is SSH port forwarding. So I'm going to show you what that looks like. Let me turn off that port forwarding rule that we already set up. I'll leave it because it's not going to do us any harm. Okay, so to set up SSH port forwarding, I'm going to open up a new PowerShell window if you're on Windows, or a new terminal window, because I'm gonna leave my SSH. Never mind. I'll just kill this and do it. So here's my SSH command to connect to my virtual machine, right? And I have the port 9999 because we have that port forwarding, but I'm going to do something else, which is using SSH to forward additional ports through the SSH connection. Okay, so if I remember how to do this correctly, it's a dash capital L for the port forward, and we're going to say, okay, on our machine, we're going to forward port, let's say 8777 to 10.0.2.15, which is our IP address on this machine here. Yeah, Neon, me too. Which is, I'm going to be very happy if I can get this right. To port 80. So basically we're saying on our local machine, the port we're forwarding, the IP address on the remote network that we're pointing to, which in this case is, we could actually do localhost as well, but I think 10.0.2.15 will work, and then port 80. So what this should do is say any traffic that I send to localhost on my machine to port 8777, and Angel, if I'm getting this wrong, please call me on it, will be routed in through this SSH tunnel to this IP address and this port. Okay, so I'm going to log in, and everything looks pretty much the same. But let me go back to here, and I'm going to try this here. http://localhost 8777. Yes. Got it in one. So again, what we've done here is we've taken this port and we've routed it through our SSH tunnel and sent it to an arbitrary IP address that the remote system can communicate with. And anybody who's going for the EJPT or the CPPT or the CPPTX or any, even the OSCP, like if you need to pivot through networks, this is essential, because what you can do, right? Let's say I'm connecting to a computer that has more than one network interface. It has a presence on more than one subnet. Well, my machine can't hit all of those networks. But if I tunnel through that SSH connection that I can establish, now I'll be able to access those other networks and be able to do things like visit a web page and run it through my Zap proxy or my Burp Suite or whatever else I want to do. So really, really, really powerful tool. Learn you some SSH port forwarding. Okay. Now, it's not enough to set up the web server. We have to learn how to configure it. So to do that, let's ls etc nginx. And this is an important instinct for a Linux system administrator, even if you're just setting up stuff to run like for you know, security purposes or doing pen testing or whatever. If you have to spin up Linux devices, you want to know how to navigate the etc folder. So here in the etc folder, we have this nginx or etc nginx. There's this nginx.conf file. There's also a folder called sites available, and both of these are pretty important. So we can cat etc nginx nginx.conf, and you can see that a lot of stuff here is commented out, but not everything. And some of the basic settings for HTTP are configured here, including the SSL protocols that you're allowing. You can set up the ciphers that you use. Oh, Angel, that's a great link. The SpecDrop stuff, that's a great, great post. So the like server level stuff is generally configured here, including how many worker connections you can have. This is how many parallel connections you can have on your server. But let's sudo vim another file. Etsy nginx sites available default. This is where the web server itself gets configured. Really, really important file. So by default, we're listening on port 80. This right here is the IP6 configuration. You can turn this off if you want. If you want to set up SSL or TLS, you would listen on 443. We can do a vhost, but we don't have to. So the way that you would do vhost, it's not like you do it in Apache, Angel. With server, you set up a server name, and that's kind of how that works. So you can set up a different server names will have different configurations. And again, the thing I love about Nginx is that it uses this very C-like syntax with the kind of blocks of code, lines ended with semicolons and blocks of code blocked off with curlies. So it makes it very easy to configure multiple components. And you can have more than one server block, to your point, right? So that's kind of how you would do a vhost, is having multiple server blocks with different server names. Yeah, so it works very much like that. And then the location, right? You can set up custom routing inside your web application. Here are your index files that it'll accept. Notice that PHP isn't on here because we haven't set up PHP yet. That's a separate thing. And then this root directive is where you point to the web root on your file system. So if I were to change this to, let's say, home, MT Taggart, site, and then save and close that, I have to make a folder, site, and then cd site. Let's vim index.html in here. Real simple. Now here's the thing. If I reload this page, nothing will happen because the configuration for Nginx is loaded into the service when the service begins. I have to restart the service in order to see changes. So to make that happen, I can do sudo systemctl and either daemon reload or sudo systemctl restart nginx. Either one is going to accomplish the task here. With that done, unless I made a very dumb mistake, nope, I see the new HTML page. So I've rerouted that server to the web root that I want. Now be careful with doing this, because depending on what you have going on in that folder, you may be messing with permissions that you shouldn't be. To that point, these files are owned by me, but the way that we actually have the real web root set up, oh wow, that's wrong. It shouldn't be set up that way. It should be run by www-data. Shouldn't be owned by root. But if we were to install some other stuff, that would change. But yeah, that is how we configure Nginx, which may or may not be one of the challenges in our challenge set. Okay. Last thing I wanted to talk about tonight, it's kind of a bigger topic because it's so much of what we do, and it was a little bit not about how you set up a Linux server, but it is about networking, is DNS, or domain name service. And broadly speaking, DNS is what is responsible for this action right here, translating a domain name that is human readable into an IP address. There is much more that it does, but it is a crucial component of modern networking. DNS it works by having records that map IP addresses to domain names. And servers can either be authoritative or forwarding, meaning that a server could either have the answer to what a domain name's IP address should be, or it should know where to forward the request to find out the answer. So for example, if I use the dig command, really cool, if I do dig for ubuntu.com, I will get back a DNS response from my own server, essentially, because this is actually cached. But, because I've accessed this before. But there are several DNS servers that exist on the internet, and one of them, for example, is 8.8.8.8. That's one of Google's. There's also OpenDNS, which is 1.1.1.1. Or is that Cloudflare's? I think that might be Cloudflare's. But yeah, bottom line, DNS, the importance. And often when things go wrong on the internet, it's DNS's fault, because easy misconfigurations can bring down massive components of the internet because of how crucial DNS is to how we do what we do. DNS is also responsible for stuff like on your own network. If you search for in a Windows environment, especially if you try like pinging like workstation 1, but you don't fill out the rest of it, it is DNS that is taking this and searching the domain for that host name and giving you a result. So I just want to call that out, that when we set up NetPlan, right, we set up name servers. And name servers are the servers that you're using to resolve your DNS. And actually, I think it was FieldDead earlier who had the question about resolveconf. You see that this name server here is 127.0.0.53. This IP address is a fudge, basically. It's a fake one that is being established by VirtualBox to do DNS resolution. But I could configure this through NetPlan to use Google's DNS servers. Let me see if I can find a really cool picture. I think it was it not? Yeah, it was in Turkey. So one trick that state governments like to do is blocking the internet. And one of the ways in which they block the internet often is by using the state-run ISP's DNS to deny access to most of the internet. But when Turkey tried this was like 10 years ago, when Turkey tried this graffiti started showing up all over the place, where they were they were telling you to configure your machine to not use the state's ISP's DNS, but use Google's DNS to get around the network blocking in Turkey. And I bring this up not just to drive home the importance of DNS, but also to point out how a lot of the things that we take for granted in terms of access to information in an authoritarian state can really be knocked down. And it's important that we have these open infrastructure tools, which, by the way, mostly run Linux, so that authoritarian regimes, for one, don't have the ability to control the information flow of their population. It's a little bit off topic, but I think it was pretty rad that DNS became important revolutionary resistance graffiti at this time. And we've seen this happen in China and in other places as well, where Iran certainly, where the blocking of DNS has been a method to tamp out dissent and information. All right. Well, friends, I think that does it for tonight's session of Hack Summer. So thank you so much for hanging out. I totally forgot to do a next time slide. So I'm just gonna vamp here for a second while I remember what next session is. Last chance for questions. Anything network-wise? Okay. Well, if not, let me quickly make this slide then. Next time, shell scripting. We are going to write some bash, and we're going to learn how to use the power of the command line that we did in session 1 in an automated fashion to do some really, really cool stuff without having to work too hard. So that will be next Wednesday. Thank you so much. No talk about BGP, Angel. Sorry. Well, we can talk about maybe doing an advanced networking session at some point. Focusing on what you need to get Linux up and running was really what I was trying to do for tonight. But yeah, thank you so much, everyone, for hanging out. Let's see if there's any place we can send you. Keep coming up dry on other streams. But thanks so much for hanging out, everybody. I'll be back on Saturday doing blue team stuff, and I will be back on next Tuesday, of course, doing red team, and next Wednesday is Hack Summer. We have 2 sessions of material left, and then there's a wrap up. So we have 3 sessions of Hack Summer left. Don't miss them. Until next time, thanks everybody.